Thanks a lot for the introduction, Dan. I'm delighted to be here. It's a real pleasure to be here. I'm excited to talk to you a bit about the work that we have been doing and some of the thoughts actually that we have. So this is an AI4OPT seminar series. So we're going to talk about machine learning and optimization. The application will be power systems. Before I start, let me just tell you a bit who we are. So as Dan said, I am from the Technical University of Denmark. So as you might know, Denmark is actually a pioneer in wind energy. So we have a department dedicated to wind and energy systems. So we have 4 different divisions. We're working all the way from materials and how the blades should be designed, wind turbine design. Then we go to wind farms, both offshore and onshore. And then we have a division about integration of renewable energy to the power systems. And that's actually where I belong. So we are about 400 people. We have 100 PhD students. And when it comes to publications related to wind energy, we are actually the most cited department in the world. We have a lot of industry collaboration, so close connection with industry. Wind energy is actually quite a big industry in Denmark. So this is how this looks like in terms of our division. We're about 100 people doing anything related to electric power systems. We are divided into 6 different sections. I am representing here the section for power systems, but also we do a lot of work with markets and data. So we have collaboration with Dan, with Pascal, here at Georgia Tech and others. So this is our group. We're about 30 people. We also have visiting researchers. One of them is visiting professor is Vasilis Kekatos from Virginia Tech. Some of you might know him. We're working. It's a very diverse group, about 20 nationalities. Okay, and we really enjoy that. What we're working on. So this just to give you an overview, and then I'm going to the topic of today's lecture. So first of all is going beyond the state of the art when it comes to new methods. We're working with Trustworthy AI. This is what I'm going to talk to you about. We're also working with quantum computing. We're the first that actually had an AC power flow run in a real quantum computer. And then we also try to develop tools that can be useful for the industry. We also do work at the lab. We're working with this also energy islands. This is the so-called artificial islands that Denmark wants to build in the middle of the sea. And then you are going to interconnect wind farms to the island and from there, the different countries. So there's a lot of challenges related to that. I'm going to use it as an example later in my talk, but there is a lot of work there. Okay. So going into the topics of this talk, first of all, I just want to thank a number of students and postdocs that have actually made this work possible. Without them, we wouldn't have something to discuss about today. And also a number of collaborators, among them Dan, that is here, but also Stephen Lowe and Gwenan Ku from Caltech, and Panagiotis Papadopoulos and his team from University of Strathclyde. Great. So let's discuss about machine learning. So power systems have been around for like 100 years or so, right? So when it comes to machine learning, the first question should be, why shall we apply machine learning to power systems? And there are actually 2 main reasons for that. Okay, the first is that machine learning tools are extremely fast. Okay, so we're talking about systems that have hundreds of thousands of variables, a lot of different scenarios. And we have to make sure that for all of those scenarios, nothing goes wrong. That whenever actually you plug your cell phone, there's enough power to actually charge it. Okay. So always assessing if a system is safe or not, this takes a lot of computational time. And there's a lot of work across the decades, actually, trying to make that more and more efficient. So make it faster. Okay. So machine learning can help there. The second is that machine learning tools can handle very complex systems and infer from incomplete data. And there is now also a piece of work coming up about surrogate models. So we tried, let's say, to learn a model, and from that actually have an approximated view of the reality that can accelerate simulations as well. So one is for assessment or estimating very fast, The other is for creating an equivalent model that's much faster. Okay. So the question, however, that people should ask, actually we have asked ourselves, is would an operator, a power system operator, ever trust machine learning methods in the control room? We're talking about black boxes here, right? So how can we actually build this trust for a safety critical system and make sure that all these stakeholders that actually deal with blackouts or the risk of a blackout every day, they are going to trust neural networks. Okay. So that will be one of the main topics, if you want, of this talk. Okay, so I'm going to talk about two challenges and one opportunity. So the first challenge is that machine learning methods are data-driven methods. So this means they're extremely dependent on high-quality data. If you don't have good quality data, you can forget about actually having a good machine learning tool. Okay. So the question is, how can actually work with that? The second is, how can we tell if the neural network has been trained to generalize well? Okay, can we trust the neural network? And then let's say the third part of this talk, by the end of it, will be this opportunity. AI4OPT is a great title for the seminar series, and for the center, I stole it and I use it, AI for optimization. So what we're going to discuss about is how we can actually convert a neural network to an optimization problem. So capture something that's impossible to capture otherwise. It's very, very complex, and convert it to a set of equations that we can actually include to any optimization problem. Why would we want to do that? So instead of actually running thousands of scenarios to make sure, let's say that, or to determine what is the stability boundary or what is the critical clearing time, let's say if we have a number of faults, I can turn that to an optimization saying, find me the maximum time it takes while my system remains safe, right? So the maximum time I can, my system remains safe for a number of different disturbances. And I'm going to give some examples there, how I can do that. Very good. So a few thoughts about that, right? So extremely dependent on data. First of all data are not the same. If you are thinking, let's say, of a neural network that would like to assess if I'm going to blackout or not, I'm much more interested in all these operating points that are close to the boundary. So if I'm really, really safe, that's fine. If I'm really, really, I'm in a definite blackout, that's fine. The question is, when do I cross the boundary from the safe region to the blackout region? That's where I need most of the data. Okay. So statistical sampling in that case is not enough. If I sample uniformly, then it's not going to give me, let's say, efficient ways to get the data I need. The second is that, and that's very, very important, the training data must follow the same distribution of your reality, right? So if, let's say, you need, when you assess your neural network, you assess it on your training and test data. If these do not reflect what happens in reality, then your neural network is actually telling you I'm having 99% accuracy for something that is not close to what will happen in reality. Okay. So it's very important to do that. And let's say if you do image recognition, then you have so many images, probably you can get a distribution that is similar. For our needs, it's a different, it's actually a much bigger challenge. So we have so many models, we have developed so many models over the past decades. So why don't we actually use these models in the neural network training, right? Instead of just trying to generate more and more data. Finally, when it comes to how can we trust the neural network, if you see a neural network optimization procedure, so training procedure, I don't know how many of you have actually trained a neural network. It's an extremely complex procedure, right? It's an optimization trying to minimize the loss function, so the deviation from the estimated output from the real output. It's a non-convex and non-linear procedure, right? So It's prone to overfitting and underfitting. So how can we trust it, right? So what we propose here is, and I'm going to talk about these concepts. The first is sampling beyond statistics. Okay. So use our physical knowledge or the knowledge of the system to sample more efficiently. Second is physics-informed neural networks. And the third is neural network verification. Okay, how can I address these challenges? So we have actually been thinking about these topics for the past 2 years, right? And we have tried to actually combine them into a framework, which we call it closing the loop, right? A framework for trustworthy machine learning. So let me talk to you how this looks like. So that's a typical way of training a neural network. So I have a training database, so I have to have some data. I'm training a neural network, then I'm measuring the accuracy. Am I satisfied? If I'm not, then I just have to retrain. And then you hope that after, I don't know, 10, 100 times you train it, you get an average performance that's actually good enough, right? So what we do here first is we want to focus, let's say, on the high information content region. This is, for example, if we're talking about stability assessment, this is exactly points that are close to the boundary, right? That's where we want to focus. So the first is we need to become smarter how we create the data, how we sample in order to get the training data. The second is that we include the physics inside the neural network training, and this means we're having physics-informed neural networks, okay? Because this will help our neural network to actually infer better or estimate better what will happen in reality if we have, let's say, a blackout or not. The third is what we call neural network informed sampling. So this means that I can actually enrich my database with new samples. This is not something new. I mean, people do that in the machine learning community. You try to enrich the database with new samples in order to improve the performance, right? And I'm also going to talk a bit about that. Then, as soon as I'm actually happy with the neural network I've trained, then I have to go and test, or let's say, verify, right? So I want to figure out what is the worst case violations I can have, how well can it predict or not. I can get rigorous guarantees, okay? And then I can have the final neural network with the performance guarantees. Now, if I'm not happy with the verification here, and my worst case guarantees are really high, what I can do is I can have another loop here, which I'm not going to talk about in this lecture, or in this talk. Actually, it's already quite a number of topics to discuss, that I can close the loop and go back here with samples that I have generated from this verification. Okay, let's try to take that step by step and see how this looks like. What I'm going to give you is an overview of these different topics. There's a much more detail if you want. You're very welcome to ask, first of all, now or whenever. You are very welcome to ask later. You are very welcome also to see the papers. Okay, the first is focusing on this high information content. So what I'm going to talk about here is, again, applications are power systems. So I'm going to combine two different security criteria. The one is the so-called N-1 contingencies. So I test for every element that can fall out and see if my system is safe or not. At the same time, I need to be small signal stable. This is, I don't know how many of you are familiar with power systems. We just convert that. We linearize the non-linear dynamic system, and we compute the eigenvalues, and these eigenvalues must be in the left half eigenspace. Okay. Good. So I need to do that for a lot of operating points, and obviously, if I do a neural network, probably I can assess that faster than checking for every operating point. The question here is, how do I generate this data? And we have a proposed approach here that's actually 10 to 20 times faster, and we have some data sets that you can actually check. What is more important for me is actually to tell you how this works. What we are focusing again is on this boundary. So this is the stable region of a real small system on a projection, so two-dimensional projection. And then this is the unstable region, the white one, and then the gray region is this high information context. So we want more and more data, or as many data as possible in this area around it, right? Okay, so how do we do that? Using convex relaxations and what we call direct walks. So let me give you some ideas. So the stability region of a power system is a non-convex region, okay? So what I can do is, please, yes, you're, yeah.
What are dimensions of this data? I mean, what are the
physically? So this is active power input. So this is the power that actually every generator is injecting into the network. Yeah, the set points of its generator.
Can you have two generators?
Yes, so it's projecting on the two generators. Actually, it's 5 in total for this specific system. Yeah, please.
Is this like an equivalent low-dimensional representation, or are you just showing two generators by themselves?
I'm showing the projection of the two. It's a 5-dimensional space, if you want to think, and I'm just, yeah, this is a 2D projection of these two. Yeah. Other questions? You're welcome to interrupt me. I know that sometimes maybe I talk a bit too fast, right? So the idea is that I'm here to, so if you don't get something, just interrupt me. Good. So here's the idea of how can make this sampling faster. We have this non-convex, as I said, stability region that we discussed. Then what I do is I have a convex relaxation of that. So I create a convex region that includes the non-convex, the actual stable region inside it. And then I just sample, right? And let's suppose that I sample a point here, and this point here is outside. Now this my approximated or my relaxed stability region. So what I do is I can get the minimum distance from this point to the convex region, and then draw a hyperplane. And this actually work we did together with Dan a few years ago. So by drawing now this hyperplane here, I can discard all those points that are here. I know already that the points that are belong to this side of the hyperplane are all unsafe. So I can very quickly classify them. I don't need to assess them. I can use them in my training database already as classified, or let's say labeled points. Okay. So I can very, very quickly at least discard large regions, or let's say label large regions of my data. And this helps a lot the speed of generating database. Now, the question is, what do I do with the points that are inside? As you see, some of them are safe, like the black ones, and some of them are unsafe. And what we do is the so-called direct walk. So we compute the gradients. And we gradually go, let's say, either from inside or outside toward the stability boundary, because we want to focus on points around here. Okay. And these gradients, we actually keep them because they are useful during the neural network training. We can actually use them inside the training since we have computed them. Okay, so and this, of course, this kind of direct walks, we can start in parallel for many different points, and then can be also much faster. So some results. This is just on a. So this is not actually parallelized. For the small system, these 14 buses, we're able with brute force to compute all the points that are in this in a close distance to the stability boundary. So this is plus minus 3%. And this takes about 10 hours with the brute force method. With important sampling, this will take about 37 minutes. So this is a statistical procedure. And with the method we discussed, it will take just 10% of that. Okay, so just about 4 minutes. Please.
So why do you construct the convex relaxation, and why do you what's the point of taking the separating hyperplanes?
Yeah. So what you really want to do is you want to generate some data, right? And this data should be, some of them should be safe, and some of them should be unsafe. Now, every time you generate one data point to enter in the training database, you have to label it, right? So operating point, then, is it that safe or unsafe? It takes time to assess every data point. That's actually the most time consuming. If I'm able to very quickly label if this point is safe or unsafe, I can actually accelerate a lot this training procedure, this generating database procedure. Is that clear?
So why do you construct the convex relaxation of the?
Because in that case, if you can see, so then I know that all points that are in this hyperplane, I don't need to assess them. I know that they are unsafe. So I can directly give them the label unsafe and pick some of them and put them in the database.
So is it computationally cheaper to construct the convex relaxation, and is that why you are constructing?
Yes.
Rather than to compare whether it's in non-convex set or not?
Yes, it is. Yeah. So yeah, this is the
dimension. How big are dimensions
of this of the data points, you mean, or the So depending now on the system we have, right? So let's say you are looking at active and reactive powers. So for in practical system, each data point should have at least, let's say, I don't know, 400 to 1,000. Yeah, it's a vector of 400,000 elements. Yeah.
Why not separating hyperplane at a tangent point with non-convex region?
Yeah.
Right.
Yeah. Yeah. Yeah.
Tim, you've got to give that convex relaxation includes the entire non-convex stable region.
Yes, because what we start here with the steady state. Yeah.
Specific.
It's the power flow, the equilibria. Yeah. Yeah. There are methods. I mean, Dan has developed some of them himself, actually. And yeah, so there are known methods over the past 10 years that do that.
And for separating
This is just a mathematical procedure, right? So you just find the minimum distance, then you have the plane that's perpendicular to that vector. Here, yeah. Okay. Yeah, and then for bigger systems, this can be also it works well. So I'm now going to a different way of enriching our database. And this is the neural network informed sampling. Okay. So again, it's very difficult to actually find where this security boundary is. So our idea is the following: we train a neural network, but we stop it a bit early, and then we just pass a lot of data through that. So just data points that we assess only with a neural network. Okay. So here, for example, in this example, we have 1 million random points. We just assess them with a neural network if they are safe or unsafe. The goal is to estimate with this trained neural network where is the security boundary. So just estimate, let's say, this region, and then we sample only 200 data points here, and we assess them. Actually, we do the we do all the mathematical let's say procedure to assess them if they are safe or unsafe, right? And we reach the database with this, and then we continue training, and we can do that until this is let's say we are satisfied with the performance or not. It's a faster procedure to actually do that than start with let's say a database of already 1 million points at the beginning. It's better to do that gradually, okay? Because you really want to focus here. It's impossible to invert this kind of actions. Clear? Let's see some results. So I have a disclaimer here that so the trend, what I'm describing is a trend, and the trend is there in all our experiments. The performance of the different methods differ a little bit in the different experiments, okay? So which one is actually performing better? So here you see that they perform the same. In other experiments, one might be better than the other, but this doesn't matter. What we're interested in here is the following. What we do is we train a neural network with 3 different dataset sizes. And here we have it, let's say, the first neural network has been trained with 5 to the 4 data points, the second 6 to the 4, and the last one 7 to the 4. 4 is because the dimension we have. is active reactive power and the control and frequency droop, the frequency and voltage droop. That's just from power systems. So you can see now what is the average loss. This is we run 100, so we train 100 different neural networks and we test what is the accuracy or the test set, the mean square error for the test set. So you can see obviously the more data points we have, the better is the accuracy of this neural network. We can achieve a similar level to twice the data points here. So this is twice the data points that we had here. We can achieve a similar accuracy if we just take the directed walks. Okay, so the first method I talked about. Yeah. So the input is active and reactive power, and it's voltage and frequency control parameters for every generator. Okay, and the output is if this is stable or unstable, so safe or unsafe. Yeah, so true, because we actually estimate the damping ratio. So for the small signal stability, if there is this ratio tells us if we are actually stable or unstable, and we need to have a specific margin. So we set that to 3%. Okay, so it's this regression. Yeah. Yeah.
I assume the viewpoints of being stable and the endpoints and unstable data.
Correct.
The ratio between them.
So depending, so if you do classification, you need to have a balanced data set. So 50-50. Okay. The problem is that the stable region is usually much smaller than the unstable region. So you have to make sure that in this small stable region, you sample with higher density. Okay, that's why uniform sampling does not work always very well. Okay. Yeah, and then you can see that the neural networking form has a similar performance for this. So for other examples, they're always lower, they're always close to, let's say, to more data points, but they might have different performance. So we need to check. Now, I want to add here that, so maybe what we can also do is physics-informed neural networks. So what we do here, we compare, again, the same number of data points as the first one, so 5 to the 4, but now have added the physical equations inside the neural network training. Okay, and you can see that this also saves us from having too much data. Or let's say we can do quite well with less data. Maybe that's the way that I should put them. So I'm going to talk now about physics-informed neural networks. Okay. So what this about? I don't know how many of you have been aware about this. So I start usually with that, which is first a little bit about neural networks. These neural networks are nothing more than an advanced form of nonlinear regression. Okay. So what happens is if we do a linear regression, we have our data points, and then we want to estimate this line, right? That has to estimate what is the output for a specific input. And then I have to determine my weights W1 and W2 to make sure that I fit the line to the data. That's exactly what happens in neural networks. Now, a recent development is this automatic differentiation, where during the neural network training, we can also have the derivatives of the output with respect to the input. Okay, we can compute them during the neural network training. So if I compute derivatives, I can include differential equations. Power systems are systems of differential equations. Okay, so I can include, let's say, the equations of motion for a power system inside the neural network training, and I'm going to show you how. Okay, so here's the simplest example one could have. This is actually a paper we had a few years ago, and we introduced physics-informed in the power systems field. So this is the standard way of training neural networks. So what I'm actually showing here is the swing equation. This is an equation of motion. Think of it, I don't know, like an equation of the motion of a spring, right? That's moving. So what I have here, again, about power systems is the rotor angle and the frequency. And I have, so theoretically, if I want to have a neural network that maps this trajectory, so this for specific power input, how the rotor angle will actually move over time. So I need to create a lot of data, generate a lot of data points along the trajectory, okay, and then train a neural network to fit that. And that's actually what this will do. Yeah, I'm losing the, yeah. So what this, the first term will do is actually will tell me that will minimize the distance between the estimated and the actual delta. Now, what I add here is also a regularization term, which should be 0. And this term is nothing else than my swing equation, okay? So when I run the neural, so during training of the neural network, I get the estimate delta, and then I differentiate that with respect to the input. Input for me here is time. And then I have this equation that actually this should be equal always to 0. So by putting that in the objective function, I have to drive that to 0, okay? So now with a lot less generated data points, I can train a neural network to actually follow the physics. And the physics is this swing equation. Okay. So what are the benefits? So we think that this can actually help as a screening tool. So at least in this very simple experiment, the neural network was 87 times faster than an ODE solver. The reason for that is that the neural network estimates the angle and the frequency of the power system for every point in time, okay? So I can just say, what will be, let's say, the frequency at t equal 5 seconds, and this will directly output the estimate. In an ODE solver, I have to integrate from t equals 0 to t equal 5 seconds to find how much will be the frequency at that point, or the rotor angle. Okay. So that's we think that this can be a good screening tool for quickly seeing, let's say, a few steps ahead, or seconds or minutes ahead of different seconds, I think ahead at least, for different contingencies.
This is a different problem from the previous. Like, the previous one was classification.
Yes, yes, true. This regression. So the previous classification, I can also do it as a regression. I can estimate the damping ratio, right? Yeah.
Are these problems related?
No, this example is not related to the other one. Yeah, it's just simpler for me to explain it like that. Yeah, but including the physical equations of whatever problem inside the neural network training is related. Okay, these are different ways of reducing the data. So, and some examples about that here is that, as you can see, so the neural network here estimates what will happen, let's say 1 second ahead. And in general, for whatever time horizon, or let's say future, we're assessing or estimating any variable like frequency, the time will be more or less the same. While with ODE solvers, obviously, as we integrate, this will go higher and higher. Great. So I'm going now to talk a little bit about verification. So we suppose that, yeah, please.
So does each neural network have its own, I guess, generator, or do you have like multiple generators and their physical models in the same neural network?
It's all generators in the same neural network. Yeah. Because it's the combination of the generators that actually tells us if something is safe or unsafe. For this example, it was actually the simplest power system possible. That's a single generator and an infinite bus, and that's why you only saw one generator. Okay. Other questions? Yeah. That's a great question. It's very challenging. So this is one of the things that we're working on right now. So there are a lot of different things. First of all, is what you really want to estimate. All the faults are completely, they have discrete events. So how many of those discrete events? So when the line trips, when, so if you want to include all, so the question first is what you want to simulate. And the second is, and the second is the size, yeah. We think that with GPUs, this will be faster. And that's why the way that at least I see it is that it's not going to replace the conventional transient stability simulation tools, but it can be a fast screening tool saying, okay, these are safe scenarios, these are unsafe scenarios. Let's focus on the critical ones and carry out the full simulation. And to be honest, now we're working with a company on this because they do this kind of offshore wind farm design, and they have these electromagnetic transient simulations. And it takes them a lot of time to do all the necessary simulations to make sure that this wind farm design is good enough. And the idea now is to find maybe ways with neural networks to accelerate this first phase of the design. Okay. Yeah. Okay. I'll talk now a little bit about verification, and then I'm going to talk about the opportunity we're saying. So this, or the next slides actually have this a central idea that's actually going to follow us for the rest of this presentation. Okay. And the central idea is that I can do an exact transformation. I can convert a neural network to a set of linear constraints with binaries. Okay, that's the central idea. If I do that, I can include the information encoded in a neural network inside a mixed integer linear program. Okay, so an optimization program. So let me tell you how to do that. So if I do that, then I can actually extract certificates for the neural network behavior. I can do worst case guarantees. I can do a lot of things. Neural networks, right? It's a set of neurons that are connected through linear weights, and in every neuron there is a nonlinear activation function. Now, the most common activation function over the past couple of years has been this ReLU. This is called rectifier linear unit. Okay, this is nothing else than a max operator, right? I can actually model that as a binary 0 or 1 and 2 linear functions. So here I have it very, let's say, I don't have any math. But the idea is that, let's say, I have one binary for every every neuron. So if the binary is 0, then I have the output is actually 0. If the binary is 1, then the output is y equal x. So this actually models the ReLU, like this one. So then I can encode all operations that happen through a neural network to a set of linear equations and binaries, right? Is that clear? Good. And then I can do a lot of things. So here is what we do for verification of classification neural networks. Okay. So here we have actually generated a lot of points. Green are the safe points, blue are the unsafe points, and red are the misclassified points. Okay. Because we really want to see if our neural network misclassifies or not. So what we do here is we start with a random point. Here we take okay. So let me see, because apparently this doesn't work. Yeah. So here we take, let's say, a random point X reference here. And what we do is we solve an optimization problem that we formulate as follows. Does the classification change if we go for any input that is actually, if we go distance epsilon from this input, does the classification change or not? If the classification does not change within distance epsilon from this reference point, then this whole area is classified as safe. Okay. Then I can certify how my neural network classifies continuous areas and not just specific data points. By doing that, I can actually get the certificates that my neural network is actually having this specific behavior. Okay, that's one idea about classification neural networks. I'm going to discuss also regression neural networks. Okay, as I told you, I'm just giving you, let's say, an overview. I'm not going into the details of each method. You are welcome to ask details if you would like to. So regression neural networks, I'm using another example, and the example is the OPF. So optimal power flow is nothing else than I minimize total generation cost, and then I have to have some constraints. There are a lot of papers, if you see in the literature, that try to estimate this optimization problem with neural networks, because they can do that 100 times faster. So I can train a neural network to actually estimate what is the optimal point of this optimization. I can do it this fast, but it offers no performance guarantees. So there's no guarantee that this actually the optimal point that my neural network will determine violates or does not violate any of the constraints of this optimization problem, which for me here is the generator limits and the transmission line limits. So what we actually devised is a method that can determine these worst case violations. And I'm going to show you some examples. So we ran that for a series of different systems. I'm not going to go through all the results. I want to focus on two of them. What do you see in the columns? The first is the empirical lower bound, which means that what is the worst case violation from all the data points that I have in my data set, right? So I have a data set, I train my neural network, which point actually results to the largest violation of my generator limits and of my line limits. And then I also determine with this rigorous method, again, converting the neural network to a MILP and formulating an optimization problem, I determine the exact worst case violation over the whole continuous region that I have defined as my input region. Okay. Please.
The neural networks optimization, are they forward or recurrent?
These are feed forward. Yes, yes, all of them feed forward. Yeah.
That worst case guarantee in the context of power.
Yes. So there's no. So imagine that you have the input is the different load realizations, right? So I can have different combinations of my loads. I have a convex space, that's my input. Is that maybe clear? I sample from that convex space. I label it, so I find what's the optimal point for every input in that space. And then I train my neural network to do that task, right? To do this optimization. Now, the thing is that I have just sampled from this convex space, but I have not covered all this convex space necessarily, right? So there are definitely points in between my samples that I have not considered, right? And then the exact tells me across the whole continuous space, what is the worst case violation? What is the largest violation of my constraints? While the other one tells me just for the points I sampled. Is that clear? No, it's actually all, it covers the whole space and in between the samples. So if you do a good sampling, you have to cover the whole boundary, right? So you have to have a uniform way of actually covering as much as possible of your space. I don't have it, yeah. Yeah, it's great. So imagine that you have a convex space. Yeah. Good. And then anyway, you sample points. Okay. And the idea is that with the exact, you can certify for the whole circle and not just for the specific point. Yeah. Good. Maybe next time. Good. So two examples here. First is for this 300 bus system. So we see that from the sample that we have in our training data set, the worst violation for the generators and the lines, the line limits is so much. If we consider the whole continuous space, this is actually 7 times larger. So there are points that we haven't considered in our training database, but now our neural network, we claim that we can apply that to the whole space, right? And can lead to 7 times larger violations. And the other very interesting result is this one, that we can actually guarantee so that there are also cases, so for the 57 bus case, that I have 0 violations, and I can actually certify to you that whatever input you have in this whole continuous space, it will, none of them will, the estimate will not violate the line limit. Okay, the output of the neural network will not violate the alignment. Okay, so that's a powerful result. I'm moving on. The next topic, the opportunity. And the opportunity is the so-called AI for optimization. As I told you, I just stole that from AI4OPT. So the summary in one slide. We can take any non-convex region. Okay, that's very difficult maybe to model, or it has maybe it's characterized by nonlinear equations, maybe differential equations, anything, whatever, you name it. Okay, if you want to have an example in your mind, this can be the stability region of a power system. So the green is safe. All the gray is the intersections of the different criteria that makes it unsafe, right? So the green is the same. I train a neural network to approximate it. So this means that I do physics informed, I generate training data samples, I do whatever. I want my neural network to estimate, this can be just a classification, when this is safe and when this is unsafe, right? Or it can be regression, so how far I am. And then as soon as I have the neural network, I can see that as a piecewise linear approximation of this non-convex region. The moment I see it like that, I can actually convert the neural network to a MILP, right? To a mixed integer linear program. And then I can embed that to any optimization. So you can think of that as this is my feasible space. It's very difficult to capture everything because it might have differential equations in there. It's very difficult to approximate that maybe in a normal optimization program. I train a neural network, I approximate that with my neural network, and I convert the neural network to the set of linear equations with binaries. I can solve whatever problem I want. Now, why is this cool? And I'm going to have an example, but I also have another one that we had actually last year at CDC. It's a conference decision control. So imagine, as I was saying, that I want to determine my critical clearing time. What this means is that I have a range of different faults, right? And different operating points. And what I want to, let's say, for a specific operating point, how much time I have maximum before any of those faults leads me to a blackout, right? So the way I would do it, and we actually still do it, is that we run a lot of scenarios, and we check when is the time that actually will lead to instability, and the shortest time is the critical clearing time. So up until this point, I can actually react. Beyond that point, it will be critical for the system. So instead of doing all these simulations, I can actually convert it to an optimization problem. I can say, find me the maximum fault clearing time while my system is still safe, right? So I can save a lot of simulations. And actually, this is one of the things that we're now trying with this company. An example. North Sea Wind Power Hub, I was talking about this offshore energy island. So this is a lot of wind farms. They can produce active power, reactive power, and they can also support frequency, and they can support voltage, right? So I have, let's say, for every, if you want a wind farm, 4 parameters, active, reactive power, and what should be the control parameters for frequency and voltage. So this is the droop coefficients, as they are called. And now, I want to find what is the permissible region, which means that what is the combination of these 4 parameters that will make sure that my system is safe. So I want to know where can I move? What is the space I can move that I can maintain the stability of my system, right? What I would do what people do actually is we just run simulations and try to check that for all the different samples I have, this maintains the stability, if you want. So here's what we do. So we can actually, again, get some samples, train a neural network. And then by converting that to a MILP, I can get, let's say, for a specific input of active and reactive power, all the permissible control parameters for voltage and frequency. Or I can actually revert that and say that for specific control parameters for voltage and frequency, I can determine all the safe combinations for active and reactive power. Okay. Yeah. And this actually brings me to the conclusions. So first, a wrap up. I talked about, let's say, 4 main concepts. First, about sampling beyond statistics. Okay, that can yield high quality training databases, and we need to find ways to improve this data generation. Second is about physics-informed neural networks. So include the physics in the training to reduce our dependency on data. Then I talked about neural network verification that can actually help us build the missing trust. And we talked about classification and regression neural networks, right, with the worst case guarantees. And then how we can convert a neural network to a MILP so we can capture intractable constraints to an optimization problem with quite good accuracy. And some of it actually, there's also some trends that like small data is the new big data, right? So there are some ideas about how to be smarter with the data we actually use or produce. What I didn't talk about, there's a number of pieces of work. I'm not going to go through them, but there is quite some work that we're doing in this area. Also some input convex neural networks and let's say training by neural network training with worst case guarantees by design. And finally, if you are interested for a PhD or a postdoc, we now have actually 2 openings for both PhDs and postdocs. If this sounds exciting to you, Copenhagen is a nice city, so you're welcome to contact me and we can discuss. Okay. Thank you. That's all.